In this video, you will learn about the chi-square. Basically, chi-square is defined in three categories known as test of independence, test of goodness of fit, and test of homogeneity. So in this video, you will learn about the introduction of chi-square, what is the contingency table, and how we can read and write the contingency table. What are the observed and expected frequencies and how we can calculate these? And what is the chi-square statistic and what is its distribution and how we can use the chi-square area table and calculation of the chi-square statistic. You will also be able to understand the assumptions and limitations of chi-square test, and you can calculate the values of test of independence, test of goodness of fit, test of homogeneity, and interpret your results accordingly. So let us start with the introduction. Chi-square basically a non-parametric test and choose to test whether the two or more variables are independent, are homogeneous, or fulfill the criteria of goodness of fit. So if our interest is to calculate, there is no association between the variables. The appropriate test is the test of independency. And if our interest is to calculate the two populations comes from the same variances or belongs to the same proportion of variance, then we choose the homogeneous test of homogeneity. And if we want to test the population has a specific probability distribution, then the appropriate test of chi-square is the goodness of fit. So it is the most popular discrete data hypothesis testing method in which we have these three categories: test of independence for association, test of homogeneity to check the population comes from same variance, and to test the goodness of fit. So now let us see the concept of contingency table. What is it? So contingency table basically is a two-way frequency table in which we can organize the data and collect it in two categories for two variables like this. This is 2 cross 2 contingency table. We can extend it to n cross n contingency table. So here we explain that 2 cross 2 contingency table. This is the variable 1, which we write here, and this is the variable 2, which we define as category 1 and 2. So how we can read the values of this table, I can write category 1, data type 1 have A observations, category 2, data type 1 have C observations, category 2 and data type 2 have D observations. So when we total this column, we can get the total data type 1. When we total this column 2, we can get the data type 2. And when we total first row, we get the category 1 count. And when we total the second row, we get the category 2 count. Here, the important to note is that we enter the number of subjects in these values. We cannot write the percentages, ratios, or average. We only write the number of subjects here. So how many subjects are included in this category? So this is only concerned with the number of subjects. So each subject can be entered only once. So here are the concept of observed and expected frequencies, which we use in chi-square statistic when we do the calculation. So we have two types of frequencies used in chi-square. One is the given or observed. So the frequencies obtained from the sample are known as observed frequencies, which are mostly given in the data series, whereas the other one, which we calculate from the observed frequencies, are known as expected frequencies. And the formula to calculate the expected frequencies is that we do the total of observed frequency, row total, and column total. Once we have the row total and column total, we multiply these two and divide it by grand total, we can get the expected frequency of each cell. And after that, we will replace the values here to get the chi-square statistic. So this is the formula to calculate the chi-square statistic. Now we have some properties or characteristics of the chi-square distribution. As we know that in normal distribution is a symmetrical distribution in which we have left and right equal area. Or we have the bell-shaped curve which is equally distributed, but chi-square is totally opposite of this. This is not the symmetrical curve. This is basically a skewed distribution in which we have positive values or the trend of positive values present in the chi-square distribution. So we can say this is not the symmetrical distribution, this is the skewed distribution and positively skewed, and the shape of the chi-square distribution depends upon the degrees of freedom. So if we increase the degrees of freedom, we can get the much symmetric curve as compared to the skewed one. Like we can see this curve in this figure. When the degrees of freedom 1, you can see a high skewed, and when the degrees of freedom are 4, the skewness still present there, and this is the positively skewed, start from 0 and end to plus infinity. And when we increase the degrees of freedom by 10, the curve is get much towards the symmetric, but not exactly symmetric. And when we increase the degrees of freedom by 20, we can see the trend of curve is totally changed or shifted. So the measures of center tendency of the chi-square distribution depends upon the degrees of freedom, which shifted with the degrees of freedom shifted. So we can say the shape of the curve of chi-square distribution depends upon the degrees of freedom, which is skewed distribution, range from 0 to infinity. And this is the positively skewed distribution. So there is no concept of negative values. So the chi-square distribution must be non-negative, or the values must be greater or equal to 0. And this is a continuous distribution as it ranges from 0 to plus infinity. So these are the characteristics of chi-square distribution in which we study. The curve is have the lack of symmetry or the skewed, and the shape of the curve depends upon the degrees of freedom. And when we increase the degrees of freedom, the curve becomes symmetric, and the values are used here are the non-negative, and the chi-square range from 0 to plus infinity. So these are the characteristic of the chi-square distribution. Now let us see some assumptions and limitations of the chi-square distribution. As this data is from a random sample, so we need a sufficiently large sample size here, at least 20 observations. So actual count data, not the percentages are readable here. So we need the actual counts instead of percentages, ratio, rate, and averages. So adequate cell size should be present in the chi-square distributions, and observations must be independent and do not have any causality effect. So this is the determination of degrees of freedom, or how we then find the degrees of freedom of chi-square, that these degrees of freedom are used here. So we have 3 types of chi-square test: independence, homogeneity, and goodness of fit. And each test have different degrees of freedom. So what is degrees of freedom basically is? Degrees of freedom is a critical factor which we use in chi-square test, and essentially the number of independent random variables are involved. That is how much independent number of variables we used to calculate the chi-square statistics. So degrees of freedom is simply the number of classes of offspring minus 1. Like there are 2 classes of offspring, purple and white, then the degrees of freedom must be 2 minus 1. That is 1. So this is the one way to calculate the degrees of freedom in chi-square test. So after identify the degrees of freedom, we have to choose the critical region of the curve, as this is the positively skewed distribution. So its rejection region or the critical region must be exist on the right tail. So here almost the critical value of the chi-square curve exists with alpha. area at the significance level. This is the table of chi-square distribution. So we can calculate the critical value from here. Like if we want to find chi-square with 6 degrees of freedom at alpha 0.05. So here we have to choose 0.05 alpha, and in degrees of freedom, we have to choose 6, and this 12.592 is our critical value, our table value for this study. So now how we can interpret the chi-square. So when the observed values are equal to the expected value, what will be the result? Definitely it gives us zero count, as zero indicates no relationship. So when the observed and expected are equal, it means no relationship. So when the larger the difference between observed and expected value, larger will be the chi-square value. So table of significance can be consulted uh, to determine if the specific value is statistically significant. Now, let us start the chi-square test of independence, or how we can test the two variables or more than two variables have some association or not. So to test the association between variables, we need the test of independence of chi-square. So the test of chi-square independence is used to determine whether the two variables are related or not. Either they are independent or not. So when two variables are not associated, scores on one variable do not depend on the score of the other. So to test this, what we need, we require the data from a random sample, independent observations, mutually exclusive measurement classes, and the average cell frequency should be greater than 5. This is the assumption of this chi-square test of independence. Here is no assumption about the shape of the population distribution from which the sample was drawn, because this is the understood that the chi-square curve is a positively skewed distribution and shape is the right tail. So to test the chi-square test of independence, our hypotheses are: null hypothesis is the variables are independent as there is no relationship between them, and the alternate is that the variables are dependent or there is a relationship between them. So these are the steps to calculate the chi-square statistics. At the first step, we have to formulate null and alternate hypothesis like this. The attribute under considerations are independent and are dependent. In step 2, we have to choose the level of significance alpha. In step 3, we have to choose the appropriate test statistic. And then we have to determine the critical region, which depends upon the alternate hypothesis. And then we compute the expected value and compare it with the table value and take the decision accordingly. We reject our hypothesis if the value exceed the table value. And if our calculated value does not exceed our tabulated value of chi-square, then we do not reject. So decision depend upon this criteria in chi-square good test of independence. So now let us take an example to clear this test. So here are the earned university degree by candidates and their hobbies. So in columns, you can see the degrees in mathematics, chemistry, and physics. And in rows, you can see the hobbies of students: music, craft work, reading, drama. So we have 4 hobbies with 3 subject degrees. And these music, math 24, this value is known as observed count or observed frequency. And now we have to calculate the expected frequency to find the results of chi-square statistics. So here we choose the formula of expected frequency, which we discussed in earlier slide, like we total these columns and these rows. After total these columns and these rows, we have grand total of 492, which is n here. So if we multiply 77 with 124 and divide it by 492, we can get the expected frequency of math music. And if we multiply 77 with 101 and divided by 492, we get the expected frequency of craft work with math. Similarly, we can calculate reading and math by multiplying 77 with 187 divided by 492. So similarly, we can fill all the values of expected frequency like this. So this is our stated hypothesis for this problem. The two criteria of classifications are independent, as the hobbies and degrees earned are independent. And in other, we can see there is no association between the hobbies of student and their degrees earned. So now we want to test it. We fill the column of this observed frequency and expected frequency. So we calculate these expected values by these observed table, and these are our expected results. Now we can write these in this column form. So this is our observed frequency column, this is our expected frequency column, and here is the formula. To calculate the values for this formula, we need to find the observed minus expected count whole square, and then we divide it with the expected frequency, and after that we total this column, and the answer becomes our chi-square calculated. So in this case, we have 54.106 answer of this calculation. So this is our calculated value. The next step in the hypothesis testing is that we have to choose the critical region, and critical region depends upon the table value. Either it lies on the, it exceeds our calculated value or lie within that region. So to break the critical region, we need degrees of freedom and alpha here. So as in chi-square test of independence, our degrees of freedoms are row -1 into column -1. Here we have 4 rows and 3 columns. So our degrees of freedom for chi-square test of independence are 6 here. So alpha is the 0.05. So in 0.05 against 6 degrees of freedom, our chi-square tabulated value is 12.592. So if our calculated value, which is this, is greater than this tabulated value, then we reject our hypothesis and conclude that there is association between variables. But if this do not satisfy the criteria, then we do not reject our hypothesis, and we said two variables are two categories, hobbies and degrees earned are independent. So this is our critical region here. If the value exists in this region, then we reject it, and if it lie in this region, we do not reject it. Keep in mind that in hypothesis testing, we use the word rejection and do not rejection. We do not use the word acceptance. And the reason is that when we increase our sample size, our results might be changed. So we cannot say this is going towards the acceptance. So we choose the word rejection and non-rejection here. So this is our rejected region, or the critical region, and this is our do not rejection region. So decision rule is according to this, as here our calculated value is the 54 and our tabulated result becomes 12.59. So this do not satisfy the critical region criteria. This falls here, not in the critical region. So we can say there is not sufficient evidence that the two criteria of classifications are independent. So we cannot say they are independent at 5% level of significance. So this is the way how we can calculate the chi-square test of independency. So next test is the chi-square test for goodness of fit, which we will discuss in our next video. Thank you.